Are ready to resume. Our next speaker is Chern from Penn State, who speaks on Euclidean billiard partitions. Shane, please go ahead.
Okay, thank you, Mel, for organizing this fantastic conference. So today I want to talk about my recent project on Euclidean billiard partitions. And of course, since we are talking about partitions, so the motivation of this work comes from a recent paper of George Andrews and his co-authors, Dragovich and Ranovich, in their study of the periodic trajectories of ellipsoidal billiards in the Euclidean space. So in the language of partition, interpret Euclidean billiard partitions as integer partitions first, we require that all parts are distinct. So we are talking about distinct partitions, and also we have two additional restrictions. The first one says that any two consecutive parts are never both odd, and also we have a restriction on the parity of the smallest part. We require that the smallest part is even. And then we define this set by this notation, D sub O cross super E. And also we have some usual notations for partitions. So suppose we have a partition lambda, and then we use absolute value of lambda as the sum of all parts in this partition or the size of this partition. And also we use sharp of lambda to denote the number of parts or the length of this partition. And in the work of Andrews, Dragovich, and Ranovich, then they first define a weight for Euclidean billiard partitions by this way, depending on the parity of the largest part. So suppose the largest part is even, then the weight is defined to be the length of the partition minus 2 times S of the partition minus 1. And here S is the total number of the odd parts. And when the largest part is odd, then we just get rid of this minus 1 term. We just have sharp of lambda minus 2 times S of lambda. So with this weight, then they discovered this bivariate generating function. So here we can see that on the left-hand side, we keep track of all partitions in this partition set or Euclidean billiard partitions. And here the exponent of X counts the weight of this partition, and then the exponent of Q counts the size of the partition. And they have a nice formula for this generating function, which is this double sum. So here we can see that in this double sum, the denominator is shifted Q factorial, and then for the numerator, we have a piecewise function depending on the parity of M. And for each case, then we can see that the exponent of X is a linear form in the two indices D and M. And also for the denominator, for the exponent of Q, we have a quadratic form plus a linear form. And also we have this Q binomial coefficient. And for the even M case, then we have a similar thing. We have a quadratic, we have a linear form for the exponent of X, we have a quadratic form for the exponent of Q, and also we have this factor of Q binomial coefficient. And the proof of their work relies on the idea of separable integer partition classes, and this concept was systematically studied by George Andrews. So here they define this weight from the perspective of the dynamics of billiards in Euclidean space. But from the perspective of integer partitions, then what we care more about is not this weight, but instead we care about the length of a partition. So a natural question is, if we replace this weight by the length of the partition, then can we have similar generating function identities? And another thing is about this partition set. So here, let's go back to the definition. So here we can see that we have two restrictions, while the second one only restricts the smallest part. So this means that the most important part of the restriction is the first restriction. It restricts the parity of any two consecutive parts. So another question is, can we just get rid of the second restriction and only consider the partitions restricted by the first one? And from this perspective, then the Euclidean billiard partitions are just special cases of this broader classes of partitions. So here we have this definition. We use D sub O cross to denote the set of integer partitions into distinct parts, such that we only have the first restriction, or adjacent parts are never both are. And we have the two generating function identities. So here we can see that we can either keep track of partitions in this larger class of partitions, or the smaller one, the Euclidean linear partitions. And here we can see that the exponent of x counts the length of the partition. So this is what we hope. And also, if we compare the two identities with the previous one, then we can see that in the denominator, we still have this Q-shifted factorial, and in the numerator, the exponent of x is still the linear form of the two indices. The exponent of Q is still a quadratic form in the two indices, and still we have the Q binomial coefficients. So for the proof of this result, then we need some combinatorial constructions. So to start our constructions, then we first need to introduce a family of operators, phi raised to a power of L. And let's say suppose we have a partition lambda, then phi to a power of L of lambda is we just add L to each part of the partition. And in particular, the empty partition acted by phi to a power of L is still the empty partition itself. So let's look at this partition: 3 plus 4 plus 7 plus 14, 15, and 16. So we first take out all parts among 1 and 2, and we have no such parts. So we have no parts among 1 and 2, then parts among 3 and 4. So we have 3 plus 4. Parts among 5, 6, we have no such parts. 7 and 8, we have 7, and etc. And 13 and 14, so we have 14, and 15 and 16, so we have 15 plus 16. And then for each block, then we can see that the first one is the empty partition. So we just treat this one as the empty partition acted by phi to a power of 0. And then 3 plus 4, it is just 1 plus 2, and then acted by the operator phi squared. So 1 plus 2 is 3, 2 plus 2 is 4. And then for all other blocks, we do the same thing. So for example, for this block, 1 plus 6 gives us 7, and then 2 plus 12, 14, 1, 14, 15, 2, 14, 16. So in other words, we can decompose this partition in this way. And then we can take out these partitions as a chain. So we have empty partition, and then 1 plus 2, empty partition, 1, empty partition, 2, and then 1 plus 2. And so here the first one is the empty partition, but we just don't care about it. And then for other partitions, then for example, for this one, then this empty partition follows 1 plus 2, and here the largest part is even. So we just add a subscript E. So this empty partition follows a partition with the largest part even. And then for this one, the largest part is 1, so it's odd. So we add a subscript O, and likewise, we still have empty partition sub O. So here from this chain, then we find that, so if we get rid of the first partition, then we have 5 types of partitions. We have 1, we have 2, we have 1 plus 2, we have empty sub E, and then empty sub O. So this means that we can define this means that we can start with a finite set of integer partitions, pi 1 up to pi 5, where pi 1 is empty sub E, pi 2 is empty sub O, and then 1, 2, and 1 plus 2. So we have the 5 partitions. And then if we use P of pi to denote the power set of pi, then we can define a map from capital Pi to P of capital Pi as follows. So the first one is the linking set of pi 1, or L of pi 1 is pi 1, pi 3, pi 4, and pi 5. So we have empty sub E, 1, 2, and 1 plus 2. And for pi 4 and pi 5, we have the same linking sets, while for pi 2 and pi 3, their linking sets are just pi 2 and pi 4, or empty sub O and 2. Now with these linking sets, then we can define, then we can construct some finite chains by the 3 rules. The first one is, say, let's say, suppose the finite chain is sigma naught to sigma capital N. Then all these sigmas are in capital pi. And the second thing is, for the last entry, sigma sub capital N, then it is not an empty partition. In other words, it is among pi 3, pi 4, and pi 5. And the third thing is, for each n between 1 to capital N, then sigma sub n is in the linking set of sigma sub n minus 1. So sigma 1 is in the linking set of sigma naught, sigma 2 is in the linking set of sigma 1, etc. And another thing we notice is exactly one of empty sub E or empty sub O belongs to the linking set for any partition in this capital pi. So let's say, so here in the linking set of pi 1, we only have empty sub E, and in the linking set of pi 2, we only have empty sub O. We only have one of the 2 empty partitions. So this means that we can extend the tilde sigma to an infinite chain in this way. So here, let's say suppose sigma n is among pi 4 or pi 5, then we just set all the entries next to sigma n as empty sub E, and if sigma sub capital N is pi 3, then we set all sigma n for n greater than or equal to n plus 1 as empty sub O. And we can see that if we do it in this way, then sigma n is the empty partition belongs to the linking set of L of sigma sub n minus 1 for any n greater than or equal to n plus 1. So we still have the third restriction, even if we extend this finite chain to an infinite chain. And then we can just include the 2 infinite chains, empty sub E, etc., or empty sub O, etc., to this set, and then we connect all these infinite chains as a set C sub capital pi. And the crucial part of this work is this number. So we can find a bijection between partitions in D sub O cross and chains and infinite chains in C sub pi, with the first entry being pi 1, pi 3, pi 4, or pi 5. And also we have such a correspondence given by the partition can be constructed by sigma naught acted by phi to the power of naught, and sigma 1 raised acted by pi phi to the power squared, etc. And also we can find a bijection between partitions in the partition set D sub O cross sub E and chains in C sub capital pi, with the first entry being either pi 2 or pi 4. And again, we have the same correspondence between the partition and the infinite chain. So I will not give a proof of this lemma, but I will give several examples. So let's still use the example 3 plus 4 plus 7, 14, 15, and 16. And we can see that this partition is in the partition set D sub O cross. And of course, we have transformed this partition into this chain as before. So we have empty 1 plus 2, empty sub E, 1, empty sub O, etc. And now the only thing we need to change is the first one. So here we change the first one to the empty sub E. And we can see that 1 plus 2 is in the linking set of empty sub E. So this chain is in the set C sub capital pi. And also we have other examples. Let's say we have 5 plus 8 plus 9 plus 10 plus 11. And again, we can transform this partition into a chain of partitions in capital pi. So we have empty, 1, 2, 1 plus 2, and then 1. So we first need to change the first 2 empty partitions as to empty sub E and then empty sub E, and then we append a series of empty sub O. So again, we have a chain in C sub pi, And likewise for this one, again, we have 1, empty, 2, 2, 1 plus 2, 1. So again, we can transform this partition into this infinite chain. And likewise, for partitions in D sub O cross through E, then we have this partition. So here we have empty, empty, 2, 2, 1 plus 2, and then 1. So we start with 2 empty partitions. But in this case, we need to change the 2 empty partitions as empty sub O instead of empty sub E for the previous examples. And likewise, for this partition, we can do the same thing. We have this infinite chain. So here from these examples, we can see how to transform partitions in the 2 partition sets into infinite chains in the set C sub capital pi. And now the next thing we need to deal with is the generating function, since we want to find the generating functions for the 2 partition sets. So let's start with an infinite chain in this set, and then we can attach a counting function for this chain. Let's say this counting function is called a kappa sub sigma, and then this function is given by this infinite product. So here we can see that these infinite chains end with either a series of empty sub E or a series of empty sub O, and the length of the empty partitions is 0. The size of the empty partition is also 0. So this means that the sharp of this value is 0. The value of this value is also 0. So this means that this infinite product is actually a finite product. And also we have another property for this counting function kappa. So from this infinite product, then we may first take out the first term for n equal to 0. Then we have x to the power of sharp of sigma naught times q to the power of value of sigma naught. And then we have this infinite product starts at n equal to 1. And we can see that this one is actually kappa of sigma prime of x q squared, where the sigma prime is a subchain, sigma 1, sigma 2, sigma 3, etc. And also this sigma prime is also in the set of infinite chains C sub capital pi. So let's just keep in mind this property, and then we will use it later. And then we can define 5 functions h1 up to h5, and they are given by the sum of the counting functions for these infinite chains. And so here, let's say, suppose we have hi, then all these infinite chains starts with pi sub I. So h1, so for h1 of x, then we sum all the counting functions for infinite chains starts with pi 1, and then for h2 we starts with pi 2, etc. And then we can see that, say we have this function hi, then this hi is this sum. And again, by the previous property, then we can just take out the first term. So we have x raised to the power of the sharp of pi I times q to the power of the size of pi I. And then since the pi j's are in the linking set of pi I, so we just count all the indices j, and then we have this part which comes from this formula, So this means that we actually have a relation between hi and then all hj such that pi j is in the linking set of pi I. And if we substitute I as 1, 2, 3, 4, and 5, then we have the 5 relations. So h1 is just h1 of xq squared plus h3 of xq squared plus h4 plus h5, and etc. So this means that we have this q difference system. And from this q difference system, then we can do some substitutions. So we can see that we can write h4 in terms of h1, h5 in terms of h1, and we can also write h3 in terms of h2. So this means that we actually have a q difference system for h1 and h2 as follows. And the last thing is the generating function for partitions in the 2 partition sets, and also the sum of the counting functions for these infinite chains. So here we record that there is a bijection between partitions in D sub O cross and chains starts with pi 1, pi 3, pi 4, or pi 5. So, and also the correspondence between the partitions and then the chains is given by this relation. So this means that the generating function for these partitions can be actually given by this sum. And if we rewrite this sum, then we actually find that this is just sum over the then the summand is just the counting function for these chains. So actually this generating function is h1 of x plus h3 plus h4 plus h5 of x. And by the previous relation, this sum is just h1 of x cubed to the power of -2. So in other words, to find an explicit form for the generating function, then we just need to find an explicit form for h1. So we will, and then for the generating function for partitions in D sub O cross sub E, then we have the same thing. The generating function is just h2 of x cubed to the power of -2. So now our task becomes finding the explicit forms for h1 and h2. And how to find the explicit form for h1 and h2? So let's first record the Q-difference system for h1 and h2. Then we have this Q-difference system, and also the generating function for partitions in D sub O cross is h1 of x cubed to the power of -2, and we call this function f of x. Then we can see that from the first equation, we can write h2 in terms of h1. So h2 is just h1 minus this guy, and then divided by x times q cubed, and then we shift it by q, and then we replace x by x q to x times q to the power of -2. And then we make the substitution to the second equation, then we just have a Q-difference equation for h1. In other words, we have a Q-difference equation for f of x, which is this Q-difference equation. And from here, then we write f of x as a formal power series in x. And of course, we can find the expressions for the first two terms. F0 is 1, and f1 is q over 1 minus q. So we can just translate the previous Q-difference equation into a recurrence for f sub n. So we have this Q-difference, we have this recurrence relation. And from this recurrence relation, then we can do one more substitution. That is, we write G sub n as f sub n times this q squared semicolon q squared sub n. And with this substitution, then we can find the expressions for G0 and G1. So G0 is 1, G1 is q plus q squared. And also we can translate the recurrence relation for f as the recurrence relation for G. So we have this relation. G sub n is equal to this guy. And the next thing, we define capital G of x as a generating function for small g. And then we can find a Q-difference equation for capital G, which is this relation. So here, capital G of x minus this guy times G of x q squared is equal to 1 plus x cubed. And finally, from this Q-difference equation, then we can find an expression for capital G. So here, the expression for capital G is this infinite sum. And for the proof of this lemma, then we only need to prove a truncated result. And so here, G of x minus this guy.
You lost your sound. So Shane, excuse me. It looks like your computer has frozen. Well, it was just the last minute of Shane's talk, but so I think we should simply thank Shane in absentia for his talk. And we start up again in a couple of minutes with our next speaker.